Now, Kw at room temperature, 1.00 times 10 to the minus 14th, and you can use more sig figs if you want, that's fantastic. But we can use this understanding and the idea that Kw is equal to hydronium times hydroxide to calculate hydronium and hydroxide at other concentrations. So as an example of this, let's say we have 0.0010 moles of sodium hydroxide and we place it in a liter of water. Well, let's calculate hydronium and hydroxide from there. Now, the reaction we're looking at, 2 waters going to hydronium and hydroxide. Now, if this was Le Chatelier's principle and we started adding in hydroxide, a product, we would predict that the reaction would shift to the left, to this side with the more liquid. So what that means then is it moves to the left, your hydronium concentration is going to go down. So this will be less acidic because you have less hydronium, and the reaction will shift to the left. So the hydronium here is going to be less than 10 to the minus 7th because you have a strong base. And what you should do is figure out an ice table for these kind of things as well. You'll only have hydronium and hydroxide. The hydroxide starts at 0.0010 moles per liter, or 0.0010 molar. They're both going to go up by X. All right, you can't have hydronium be 0 or negative, so it must go up by a little bit. So that's going to make it plus X for each of them, and then equilibrium, hydronium will equal X, and hydroxide will be 0.0010 plus X. You can let those equilibrium parts, let them equal to Kw. Kw equals X times the quantity 0.0010 plus X. And this reaction as written right now is a quadratic formula because you'd end up with X squared plus 0.0010X minus Kw equals 0. And that's a totally cool way to solve it if you have a solve button on your calculator, for example. However, because the X, which is the amount of hydronium made, is going to be so much less than 0.0010, all right? I mean, it was already 0. It's going to go up a little bit, but it certainly isn't going to go up that much. So what usually is done is you can ignore the plus X. That little plus X can often be ignored. Well, if that's the case, then hydroxide is 0.0010 molar. So you end up solving for hydronium. Hydronium equals Kw divided by 0.0010. And it does come out to be a small number, 1.0 times 10 to the minus 11th moles per liter. So in the last problem, we found that hydroxide was 0.0010 moles per liter, and hydronium was 1.0 times 10 to the minus 11th moles per liter. So both small, but the hydronium, of course, is especially small. Chemists consider this solution to be basic because the amount of hydroxide, the actual number, 0.001, is greater than the amount of hydronium, the 1.0 times 10 to the minus 11th. So in this case, scientists would consider this solution basic. So more hydroxide means base, more acid hydronium means acidic. Chemists are easier, though, with using what's called the pH scale. And pH is just a transformation you can make on your hydroxide and hydronium to give you better values. So pH equals minus log the H3O plus concentration is a pretty important equation. It represents a way to quickly get just a number for the amount of acids that's present. And you always have to figure out hydronium, but it works for bases as well as it does acids. It's a pretty cool relationship. In a neutral solution, we saw that hydronium and hydroxide were both equal to 1.0 times 10 to the minus 7th moles per liter, and that's cool. What is the pH of that, Dr. Russell? Great question, random student in the back of the room. pH is minus log hydronium. So minus log 1.0 times 10 to the minus 7th, that gives you a pH of positive 7.00. So 7.00 is the pH of neutral solutions. Nothing else has happened with them. They're just totally neutral, and it's pretty cool. Soren Sorensen was the first person to create the pH scale. I think chemists like the little O with the line through it, so they just like to show off or something, but still pretty cool. Okay, so here we want to find the pH of a 0.0010 molar sodium hydroxide solution. No problem. So what we need for figuring out pH is we need hydronium, not hydroxide. And earlier we calculated how the hydronium would be 1.0 times 10 to the minus 11th moles per liter. That's the number we need for pH, not hydroxide, but hydronium. So minus log 1.0 times 10 to the minus 11th, that comes out to be a pH of 11.00. What this means then is that in general, a basic solution will have a pH greater than 7. So in the sodium hydroxide solution we looked at earlier, the hydronium was that 1.0 times 10 to the minus 11th, which is a lot less than the 0.0010 number we started with. So more hydroxide than hydronium, that means the solution is going to be basic, and we can see by the value of pH of equal to 11, you bet it's going to be basic. Anything greater than 7 should be a base. Now, neutral solutions technically are just for pH of 7, or pretty close on it, depending on who you talk to. But the closer you are to 7, the more likely it is to be neutral. And the acidic solutions have pHs which are less than 7. They're going to have more hydronium than hydroxides, and literally the number will tell you if you have more hydronium or more hydroxides. pH is less than 7, more hydronium, so that's acidic. pH is greater than 7, will have more hydroxide. Those solutions are basic, and right around 7, it'll be neutral. In this question, we have a solution with a pH of 10.5, and we want to know, is it acidic, basic, or neutral? It might be lame, it's true, but that's not a valid answer here, so just ignore that. Anyway, literally look at the value of pH, and pH is greater than 7, i.e. 10.5, those are going to be basic. If your pH is less than 7, for example, 5.5, that would be acidic, and if it's equal to 7 or very close to 7, that's when it's going to be neutral. So pretty easy to find out. In the picture on the right, we have a Diet Coke solution being analyzed by a pH meter. pH meter is just an electronic device that allows you to find how acidic or basic something is. And you can see in this example with that pH probe in the Diet Coke, pH comes out to be 3.12. So because the pH here is less than 7, we would call this Diet Coke acidic. And most compounds and drinks that we eat and consume, most of them are actually a little bit acidic. Now, because the pH equals minus log of hydronium, we can calculate how much hydronium is actually present. And the hydronium, like all things in square brackets, will be in molarity. So let's calculate the moles per liter of the hydronium. So what you want to do is take the anti-log of both sides. Now, the pH is 3.12, and as you can tell, if you put the negative on the other side, you're going to get 10 to the minus 3.12 equals hydronium. Now, the anti-log for base 10 is just 10 to the x. So 10 to the power of log H3O plus is just H3O plus. On the other side, you do something to 1, you have to do it to the other side. So 10 to the minus pH is where the 10 to the minus 3.12 came from. This comes out to be 7.6 times 10 to the minus 4 moles per liter of hydronium at that particular set of conditions. In this problem, we have a pH of 4.50, and we want to solve for the hydronium, the H3O plus concentration. No problem. So hydronium equals 10 raised to the power of minus 4.50 when you figure it out. And in your calculator, and this is definitely a job for your calculator, this comes out to be 3.2 times 10 to the minus 5, or answer B. So that's what's kind of cool about this. It's easy to find hydronium from pH, and all other things will follow shortly as well. Now, we haven't talked about sig figs and logarithms yet, and we need to do that real fast because we're going to use a lot of logarithms. So in general, when you have a logarithm and you want to take the log of a number, you're going to use n sig figs for every n decimal places after the decimal. And it's easier just to show examples of this. So here are 3 examples of using sig figs. The first 2 are outright logarithm calculations. Now, the log of 3.07 times 10 to the minus 3, that's a 3 sig fig number. So we want to record digits 3 places to the right of the decimal. So minus 2.513 would be the correct number. And you can try this in your own calculator. You wouldn't raise it to minus 2.6 or something like that. You want to keep 3 sig figs, which means 3 digits past the decimal. Now, log 1.1 is a 2 sig fig number. So you can see there's 2 red numbers to the right of the decimal, which is kind of cool. And then finally, 10 to the minus 3.12, the 1 and the 2 are going to be our sig figs. We're doing an anti-log. Remember, all the anti-log is the number of sig figs past the decimal. So in this case, that would be 7.6 times 10 to the minus 4. Nothing you can't do, a little bit weird, but anyway, now you know what's going on. Most food and drinks are slightly acidic, and most household cleaners are somewhat basic. So up in that chart in the upper right there, you can see the pH values of different compounds. And the acidic part, i.e. the numbers less than a pH of 7, things like water, coffee, orange juice, wine, stuff like that. Lime juice is pretty acidic. On the other hand, the things that are greater than 7, the basic parts include things like ocean water, baking soda, milk of magnesia. A lot of the household cleaners have ammonia, NH3, so that's there. Sodium hypochlorite, NaOCl, is actually a base as well. So lots of examples on both sides, and we'll see more and more of these as we go through the course. We saw earlier how pH equals minus log of the hydronium, essentially minus log of H+. But in reality, you can have any kind of px scale where px equals minus log the concentration of x. So if you know how much you're starting with, then you can find the px for that value. We're going to talk in a little bit about pKa. Now, we saw some Kas earlier. We're going to talk more about Ka, and pKa is minus log of Ka. We'll come back to this in a little bit, but just kind of keep that in mind. pKa equals minus log of Ka. pOH is another thing we'll use. Now, pOH is related to the hydroxide. So pOH equals minus log of the hydroxide concentration. And if you wanted to find hydroxide, you'd go 10 to the power of minus pOH, etc., etc. Kw equals hydronium times hydroxide, which equals the Kw value 1.000 times 10 to the minus 14th at room temperature. Well, maybe you want to find something out from there. If you take the negative log of both sides, you get negative log 1.000 times 10 to the minus 14th. And that equals minus log of H plus and minus log of hydroxides, because hydronium times hydroxide, if you do the logarithm of that, it comes out to be negative numbers. But anyway, at the end of the day then, you end up with this expression, minus log of 10 to the minus 14th is 14. That equals minus log of hydronium, which is pH, plus minus log of pOH, all right? And so if you know these kind of things, you can find one from the other as long as you're about room temperature. And if you ever do studies where you're away from room temperature, you may have to double think your math to make sure that you're right, stuff like that. pKa, which is minus log of Ka, plus pKb minus log of Kb equals 14. And that's kind of cool. Now remember, Ka is the equilibrium constant for an acid. Kb is the equilibrium constant for the base. And most of the time they're under 1, so they're reactant favored. 14 equals pKa plus pKb. That's going to be pretty important to us coming up. We have a solution with a hydronium concentration 3.2 times 10 to the minus 5. What is the pOH? Okay, hydronium is H3O plus. OH minus is hydroxide. So we need to translate the hydronium concentration into hydroxide to answer this question. And there's a couple different ways you could do it. What I would probably do here is I would first solve for hydroxide, because Kw equals Ka times Kb, but Kw also equals, as we saw, hydronium times hydroxide. So if hydronium is 3.2 times 10 to the minus 5, and we want the hydroxide ion concentration, then Kw divided by 3.2 times 10 to the minus 5 should give you the hydroxide value. And once you have hydroxide, minus log of hydroxide will give you pOH. So let's look at how that works out. So here's Kw divided by hydronium, 10 to the minus 14th divided by 3.2 times 10 to the minus 5, and all of that equals the hydroxide concentration. So once you have hydroxide, then minus log of hydroxide will give you pOH, and you can tell we're good to go on that, which is kind of cool. A way to check yourself is that the pH of a basic solution should be basic, i.e. the pH should be greater than 7. And you can see on that list up there, C, D, and E are all acidic or neutral, so that's not very helpful. Now, A could be a base, but that would be pretty powerful. Most bases fall off a long time before 14, and that value is 18, so that seems a little unreasonable. Litmus paper can be used to tell if you have an acid or a base in solution. Now, earlier I showed a picture of a pH probe, and honestly, that's probably a better way. However, litmus paper will do the same thing. And the litmus paper has colors associated with it. So if you have kind of like a red color or that kind of off orange color in the upper left-hand corner, that means you have an acid. On the other hand, if you have kind of a blue-purple kind of color, that means you have a base. So we're going to go through some relationships here to think about how these acid and base things kind of operate. An acidic solution will have a pH less than 7, all right? That's no problem. But a pH less than 7 means acid, and that means acid, the hydronium, will be greater than the hydroxide, the base part, all right? So hydronium will be a bigger number, and hydroxide will be a smaller number. And pOH being really small, even for these kind of things, pOH is going to be very, very large. It's not going to be very strong. Remember that low values of pH and pOH mean strong. So a low pH would be more acidic. A high pOH would be less basic. That's kind of how this part works out. For a basic solution, it's the opposite. For a basic solution, you'll have a large pH, a pH greater than 7. But bases mean you don't have a lot of hydronium, so that'll be low. But bases do mean you have a lot of hydroxide, so no problem. And then finally, if you have a lot of hydroxide, your pOH will be down. So that's kind of how this works in terms of acids and bases. What you need to remember is that Kw, hydronium times hydroxide, that's always going to be a constant. And for us at room temperature, 25, it's 1.00 times 10 to the minus 14. So that'll help you to understand how these things go around. And also remember that pH plus pOH equals 14. So if pH goes down, pOH is going to go up. If pOH goes down, pH is going to go up, et cetera, et cetera.